Okay, well, welcome back, everybody. Just a quick note. Obviously, today we'll finish the last chapter. It's very short, and so that leaves Thursday as a study day. You might check the schedule. And next Tuesday is exam number 5, also a study day on that day, and then that following Thursday. So basically, you got three study days. So that's a good opportunity to come in with any type of questions. Um, Excuse the background sound. You might my little one in the background. I'm kind of babysitting here for the next 5 minutes, so bear with me if you hear her in the background. Anyway, any questions? Everybody knows what's coming up in the next couple of weeks. No surprises, right? With respect to assignments, if you've not completed some of the assignments, they're open. Everything's still open past assignments. It's still open until the 14th. Now, the 14th is the last day for anything to be turned in. Okay, now, so that includes the final. If for some reason your work schedule doesn't allow you to be able to do your exam on that or whatever schedule you have on that day, I can go before, but I can't go after the 14th. Okay, so let me know now if you need accommodations to do the final exam before. Let me see. Don't forget your assignments, the ones that are left. But like I said, I was going to say, they're still open, even the ones you did that you may not have done in the past. They may be a 0 there, but they're still open. On the homework has 2 attempts. You can go back and knock them out. And there is a penalty, however, but some points is better than no points, okay? Also, if you go back and you do the second attempt on previous assignments for the homework, for example, Canvas thinks they're late, but obviously if you did it on time the first time and you want to go back and do the second attempt to maybe improve your grade a little bit, your points that is, and if Canvas treats it as late, let me know and I will correct that. Canvas can understand that. Yeah, you did it on time the first time, you're coming back the second time, you should not be penalized for that. Okay, so any questions? Yeah. All right, well, with that being said, then let's jump in. Okay, solutions. We're going to talk about coffee. Now, solutions. Normally when we talk about solutions, we're talking about liquids, but we're going to learn here that solutions are can be other combinations, can be solids. More on that here in a bit. So how do we define a solution? Okay, basically a solution is defined as a solute dissolved in some type of a solvent. Now, the solute is whatever chemical is present in the smaller amount, and the solvent is the chemical present in a larger amount. Okay. Now, as I said, we're using the word solvent, but you'll learn here in a bit that it could also be a solid. So, well, most of the time we're dealing with water as the common solvent, but bear in mind, we can deal in water, as I stated before, is a polar solvent. There's non-polar solvents. Now, the thing to remember is this: like dissolves like. So that means polar solutes will dissolve in polar solvents. The converse is true, that non-polar solutes will dissolve in non-polar solvents. Okay, so water is not always the solvent that one could be utilizing. Okay, so concentration, and I think this part is pretty self-explanatory. You can tell about the color of these glasses, that on the far left, you have a color solution, which is very dilute compared to the one on the far right. Basically just telling you that the one that's concentrated just has more solute in that solution, okay? And the dilute solution has, less solute. All right, so what are some of the examples? What are some of the physical states of solutions? Well, we can have a gas in a liquid. For example, carbonated drinks is a solution. You can have your soda pop. You get that fizz and that bubbling going on in the liquid, okay? Another example, you can have a liquid solution where you can have like a mixed drink, okay? A lot of things, coffee, tea, or a liquid, well, okay. I shouldn't say tea because you started with a solid, but there's a lot of liquid examples of solutions. Mixed drink, for example, is the most common one. You could have a solution where you have a solid dissolved in a liquid. So again, here you can have like salt water, taking things like sodium chloride, which is ionic, and you dissolve it in water. But you could have a nonpolar solute and put it into, let's say, a nonpolar solvent. So water's not always a user. You can have things like hexane, which is a liquid and it's nonpolar. You can dissolve other things. You can have like a gas-gas combination. Okay, air is a good example of a solution. You have the majority of your gases, nitrogen and oxygen, but then you have the dilute amounts of trace amounts of other gases, the carbon dioxide, a variety of different gases. So solid. Okay, steel. We may think that steel is just iron, but it's not. Steel is an alloy, meaning because if we were to use iron by itself, pure iron, it just does not have the strength to be used to build buildings with. And so steel is a combination of iron with some carbon in there. Brass is another example. Brass has, bear with me. Brass is a combination of copper and zinc, okay? Copper in itself, pure copper in itself is extremely soft metal, but you add zinc to it along with some other trace metals and it becomes harder. Gold, the jewelry that we utilize is not pure gold. Pure gold, like iron and the other pure metals, are very soft. And so we put in there other metals to strengthen them up, okay? All right, now keep in mind, like I stated, like dissolves like. So a polar solute will dissolve in a polar solvent. And the nonpolar solute will dissolve in a nonpolar solvent, okay? Like dissolves like. So a classic example, we know that nonpolar and polar do not mix. Classic example is oil water. We get an oil spill. Oil is very nonpolar. Water is polar, okay? They're not gonna mix. Italian dressing is another example. A bottle of Italian dressing has two layers. You have an oil layer and an aqueous layer, okay? They do not mix, too. When we're dealing with liquids and to describe them, that liquids do mix with each other, we say that when two liquids mix, it is miscible, okay? When they do not mix, because maybe of polarity, they are immiscible, okay? Immiscible. So if a solid is dissolved in a liquid, then its term is soluble. If it does not, it is insoluble. Now, if we're dealing with ionic compounds, okay, we're going to be dealing with aqueous systems, and the solubility of ionic compounds is defined by the solubility rules. And we know that something is soluble or insoluble, okay? Now, even though it is insoluble, even though it's classified as insoluble, it's still a little bit of it still in solution. Just a little bit, we talked about that, but the bulk of it is insoluble. My apologies here, somebody's trying to get my attention. All right, so here we have a table where we have on the first column, we have a solvent. And we're given the formula, NH3, C12H26, and Br2, okay? Then across the table, we have the solute. Now, before we do anything, we have to define the polarity of all of them. So we have to look at each one and determine, is it polar or non-polar, okay? So recall some of the rules about the polarity of molecules. When bonds, chemical bonds are non-polar throughout the molecule, the whole molecule is non-polar, okay? When chemicals have polar bonds that do not cancel out, okay, then that molecule is polar overall. When the polar bonds cancel out because of their configuration, then we end up with a nonpolar species. So we go back to let's say Lewis dot structures to help us determine whether a molecule is polar or not. If we look at NH3, we talked about ammonia at, oh, my mouse, my pen has stopped working. Bear with me. There it is. Okay, now if we look at NH3, that is ammonia. We talked at length about this. We did the Lewis dot structure. And if you recall from the Lewis dot structure, we came up with this particular structure. Okay, it had a lone pair. And this gave us the general formula of AB3E. Okay, now we do have three polar bonds. Okay, drawing the arrow in the wrong direction, where the dipole is going from the hydrogen to the nitrogen. Okay, and it does that because we know that nitrogen is a lot more electronegative than the hydrogen. So we have three polar bonds. Now we would think that based on this, having the lone pair and three bonds, it would have a tetrahedral configuration. For example, something like this. To recall the tetrahedral configuration drawing that I've drawn in the past, where we have four polar bonds on here, okay, because A and B are different elements, four polar bonds, but because of the configuration, because of the symmetry of a tetrahedral, this species here is nonpolar, okay, because the polar bonds all cancel out. While over here with ammonia, that's not the case, because the lone pair take up a lot of space. And therefore that bond angle now is much smaller than the standard 109.5 degrees, okay, resulting in a polar molecule. And that's why I stated that whenever you come up with the Lewis dot structures and you end up with a lone pair on the central atom, 99.99% of the time you have a polar species, okay? Always at 99.99 because nothing's ever 100%. Okay. And so the result is that ammonia is a polar molecule, okay? Now, when we look at the next one, C12H26, can be anything. With 12 carbons, there's almost an infinite number of configurations that molecule can have. So it's hard to say you can say it is a particular specific compound. But what you can say is this. If you recall that all carbon-hydrogen bonds, all of them are nonpolar bonds. Okay, and so all we have in here is nothing but carbon hydrogen. Therefore, having all nonpolar bonds in your structure results in a nonpolar molecule. So C12H26, not even knowing what structure it is, we know that it is simply nonpolar. Okay. Then we have the Br2 or bromine. Bromine is diatomic, okay? Being diatomic, you've got two atoms of the same atoms combined there. So therefore the electronegativity is equal. Therefore you have an equal sharing of that bond. Therefore, you have a nonpolar species. Okay. And so the general formula that I have to, when we're talking about bonds, is I utilize the AB scenario and the AA scenario, where AA means the two elements are the same. When the two elements are the same, then we have a nonpolar bond, and the whole molecule they have, that's all you have in that structure, nonpolar bonds, you have a nonpolar molecule. Remember that carbon hydrogen fits in this category because the electronegativity of carbon and hydrogen are essentially the same, and therefore the net result is a nonpolar bond. The other general description was I wrote AB. AB, two different elements. Automatically, you can say, I got a polar bond. I got a polar bond. Now, do I have a polar molecule? But that depends. If the polar bonds do not cancel out, then you have a polar molecule. Okay? If they do cancel out, then you have a nonpolar molecule. So you have, two possibilities when you have polar bonds. Okay. All right. So if you keep that to help you out, that'll help you out to determine and to assign whether the molecule is either polar or nonpolar. HCl is the example of the AB. Okay. So hydrochloric acid is polar. Okay. I2, like bromine, this is iodine, diatomic, that is nonpolar. Okay. PCl3, phosphorus trichloride. Well, we may not know what it is, but tell you what, do the Lewis dot structure. Okay, go refresh your memory. Phosphorus is a central atom, on how to do the Lewis dot structure, and guess what? You're going to come up with this type of species formula. Okay, which is very similar to the ammonia, which is AB3E, and you got a lone pair. The fact you got a lone pair right in the middle, central atom, you don't need to go any further. You have a polar species. Okay, and then as the case of C12H26, we have here carbon and hydrogen. That's all you see. Nonpolar bonds, so that species is nonpolar. Now, once you have defined the polarity of the molecule, now you can answer the question whether the solutes will dissolve in that particular solvent. And keep it in mind, like dissolves like. Okay, so we have HCl and ammonia. Yes, HCl will dissolve in ammonia because both of them are polar. Okay, iodine and ammonia, no. Okay. Because we have a nonpolar iodine and a polar solvent. The phosphorus trichloride, yes, it will dissolve because they both have the same polarity. CH4, which by the way is methane, and ammonia, no, simply because of the differences in their polarity. And going down with the next batch, we have a no for hydrochloric acid and C12H26, again, because of difference in polarity. A yes for the iodine, okay? A no for the phosphorus trichloride, again, because of polar solute and a nonpolar solvent. And a yes for methane, okay? Because again, both are polar, nonpolar, excuse me. Bromine, be a no for hydrochloric acid, a yes for iodine because of polarity, a no for PCl3, again because of polarity differences, and a yes for methane, okay? And so to fill out these type of tables, to rehash what we just stated, you first define the polarity of the molecule, and if you need, utilize the Lewis dot structures to help you come up with a structure, okay? Identify the polar bonds. Not only that, because now with this, you can also define the IMF. Remember the last chapter we talked about IMF? We know the HCl will have dipole-dipole interactions. Okay. I2 will have London bridges. Okay. PCl3 would have dipole-dipole. CH4 up here would have London bridges. Okay, so that also aids us once we learn the polarity molecule to assign IMF interactions and also to determine whether the solute will dissolve in that particular solvent. Okay. Using the terms miscible, immiscible, soluble, insoluble, again, miscible and immiscible deal with liquid and liquid. So we have a polar liquid and a polar solvent. Yes, it would be miscible, whereas it would be immiscible if we're dealing with a nonpolar solvent, which is compared using a polar solvent, a polar liquid. Nonpolar liquid, immiscible with a polar solvent, miscible with a nonpolar solvent. Polar solid would be soluble, okay, with a polar solvent, and insoluble with a nonpolar solvent. Nonpolar solid would be insoluble with a polar solvent and soluble with a nonpolar solvent. Ionic compound depends on the solubility rules when we want to define whether something will dissolve. If it's an ionic compound, we're looking at water, an aqueous system. You won't see a ionic compound with a nonpolar solvent. It just wouldn't occur. You may have noticed this maybe at home when you were cooking, you put a little oil in the pan, maybe you throw some sodium chloride, right? You put it in the pan with the oil, heat it up, that sodium chloride will not dissolve, okay? Try it with a little bit of water, it certainly will, okay? Sodium chloride obviously is soluble in water, but it is not soluble in oil because of the differences in polarity. All right, so the dissolving process, not much to say here other than the water molecules. When we talk about dissolving, we are generally talking about an aqueous system with an ionic compound. And so here we got a sodium ion. It could be sodium chloride, it could be anything. But you can see here that the sodium is solvated with the water molecule, the partial negative of H2O. Recall that this H2O water is very polar, and there is a partial negative on the oxygen because the oxygen is a lot more electronegative than the protons. And so the protons, the hydrogens have a partial positive. And so on the other side, maybe if this is sodium chloride, you will see the chloride ion being solvated in that direction. So this is a big old three-dimensional matrix when you get ions in solution, okay? All right, so not much more to say about that. But let's talk about concentration since we're dealing with solutions, okay? We're gonna only deal with two types of concentrations, which are a measure, a calculation actually. So we have what's called mass percent, which is a ratio of the weight of the solute divided by the total weight of the solution, okay? The weight of the solution is the weight of the solvent and the weight of the solute. And we multiply that by 100 to give us the percentage, okay? Then we have molarity. Now we introduced this a while back when we were talking about pH and we were talking about the proton concentration. Remember that? We had the proton in the brackets. That was molarity. That was that's what the brackets meant, which we had moles per liter. Okay. So moles means that we're probably gonna have to need the molar mass of the compound, because we're probably going to be given grams and we need to convert that grams into moles. That means we need the molar mass. Well, the molar mass, if you recall, is we sum up all of the atoms involved in structure. That is, we sum up their atomic weights. that gives us the molar mass, and the units of molar mass are grams per mole. So if we're given grams, we can divide by the molar mass to give us moles, okay? And the volume is in liters, so if the problem gives you the volume in liters, you're good to go. If not, it could be milliliters. Well, if it's given in milliliters, remember, 1 liter is equal to 1,000 milliliters. So that factor we would utilize to convert the milliliters into liters, okay? All right, let's do a couple of examples. All right, so by definition, as I stated, mass percent is the mass of the solute, okay? Oh, let me check. Okay, the mass of the solute divided by the mass of the solution times 100. Keeping in mind that the mass of the solution is the mass of the solute and plus the mass of the solvent. So in this example, they're asking to calculate the mass percent if you take 15 grams of potassium nitrate and you dissolve it in 135 grams of water, okay? Bear in mind, when we're looking for mass percent, we don't really care about the molar mass of the material. Mass percent is simply the weight of whatever solute you're given. No concern about molar mass. We don't have to come up with the formula for potassium nitrate. We're given 15 grams, so we set up the problem where we take 15 grams plus 135, and that gives us the mass of the solution, and then we got 15 grams divided by that total weight, okay, times 100, and that tells us we have a 10% solution, 10% solution, okay. Those of you working with, in the medical field or working for that degree, you may be familiar with saline solutions. Saline solutions are a 0.9% sodium chloride in water, an aqueous system. That is a mass solution ratio times 100, 0.9%. It has to be 0.9% because anything more concentrated or anything less concentrated, when that goes into the blood system, the difference in concentration can either cause your cells to burst or shrink. So it's very important to maintain that salt solution concentration. Okay. Now, occasionally, we may not know, for example, here we're given the amount of water that we need, but you may be given a problem where you need to calculate the amount of water you need to make an X% of an X amount of some chemical. And that's what this problem says. It says here, how many grams of water are needed to make a 5.00% saline solution if I have 10 grams of salt, okay? 10 grams of salt. So we set that problem up as follows, okay? Because we know that the solute is 10 grams. We know that we're asked to make a 5% solution, 5.00%, and we don't know the amount of water. So we set that equal to X, because this ratio times 100 would give us 5% if we know what X is, okay? So what we have to do here is essentially solve for X. So it's probably the most complicated algebra you probably have to do, and that's it. We're not going any further with algebra, but that's about it. We're going to solve for X. Now, you can solve for X. There's a couple ways to do this, all right? And one way is to, let me clear my mess up a little bit. You can see you have the quantity 10 plus X in the denominator, okay? We can multiply 10 plus X on both sides of the equation. Okay, so if we multiply by the quantity of 10 plus X over here and 10 plus X over here. This cancels the 10 plus X in the denominator, resulting in the following. Right there. Okay, so that's your first step. Okay. Now here you could do any number of things here, but what the book is going to do is simply take the 10 and multiply it by 100. Okay, that gives you 1,000. So there's the second step right there. Again, you can do this in multiple ways, but what they're going to do here is they're going to divide through by 5. Okay, and in doing that, you get rid of the 5 on the left side, and now you have, oh, let me clear this up, sorry. Now you have 10 plus X is equal to 1,000 divided by 5. Okay, now next step, obviously, number of things you can do. Go ahead and take 1,000 and divide it by 5, that's 200. Now you've really simplified it. Now you've got to isolate X. So if you do a negative 10 on both sides of the equation, you end up with 190. Okay, X is equal to 190. Now we put it here in scientific notation simply because of sig figs. Sig figs here, we got 3 sig figs, 3 sig figs over here. So our answer should end up with 3 sig figs. If we give the answer at 190, it's only 2 sig figs. Okay, so by putting it in scientific notation, there's no question, it is in 3 sig figs. Now, if you write it as 190 and you had the decimal point, I would accept that as 3 sig figs. Okay, because by definition, that's true. It's 3 sig figs with a decimal point. All right, so now how do you know this number is correct? Well, you take the 190 and you plug it back into X and you solve the equation, and it should be 5.0 is equal to 5.0, which is a true statement. 5 does equal 5. If you plug it into X and you come up with something else and your math is correct, then obviously something happened along the way, and if that doesn't equal to 5 on both sides, it's something went amok in your calculation. You go back and check your numbers. All right, so that says that if I take 190 grams of water, 10 grams of salt, I mix them up, I end up with a 5% solution. In this case, a salt solution. It could be any salt, but. All right. How about molarity? Let's do a couple examples of that. All right, so by definition, molarity, capital M, is defined as moles per liter. Okay, moles per liter. So first question asks is calculate the molarity if I take 9.9 grams of potassium bromide and I dissolve it in 2.5 liters of a solution. Okay, 2.5 liters of water. Well, since I'm starting with 9.9 grams of potassium, don't take 9.9 grams and divide it by 2.5. That is not molarity. Remember, you got to calculate moles. Well, to calculate moles, we need the molar mass. Well, before we need the molar mass, you need to write the formula, the correct formula. And so we have potassium bromide. Okay, it's an ionic compound. So potassium is in group 1 metal. It will have a +1 charge. Bromide is a group 7 nonmetal. It will gain 1 electron. So it has a -1 charge. Therefore, the formula for this is simply a 1-to-1. So it's KBr. And that is the formula for potassium bromide. Now that I know that, I can look up the atomic weight for potassium, the atomic weight for bromide, add that up, and that gives me the molar mass for potassium bromide. and I take 9.9 grams and divide it by the molar mass, that gives me the number of moles of potassium bromide. Note my units here, grams cancel, okay? Now, keep in mind, you have 3 sig figs here, 3 sig figs here. So our answer should have 3 sig figs if we're done. Notice that our numbers here, we don't truncate. So you use the full numbers that are given to you in the calculator. Don't truncate, don't do anything or round it up or anything until we get done at the end of the calculation. So 9.9 grams divided by 119.00 grams is equal to 0.08395 moles of potassium bromide. We divide that by the volume we're given, 2.50 liters. And now our concentration is 0.0336 moles per liter. And that is the molarity of 9.9 grams dissolved in 2.5 liters of solution of water. Okay. All right. There are worksheets, obviously, and so examples. So the more you do, like any calculation, the more familiar you are with the calculation, and the easier it is after a period of time to do these type of calculations. Practice, practice, practice. Let's do one more. Okay, we're calculating the molarity. What is the molarity if you take 5.0 grams of sodium phosphate and you dissolve it in water to make 255 milliliters of solution? Okay, well, first things first, I'm going to see that I got 2 sig figs here, 3 sig figs here. So my final answer should be, it should have 2 sig figs. That's my final answer. All right, so I got that on the way. So I keep all the numbers until the end, and then I truncate it at the 2 sig fig position. All right, sodium phosphate. I need the molar mass. Well, before I do that, I need to write the formula. So like as we've been doing before, we know that sodium is a group 1 element, specifically a metal, is group 1. It has 1 valence electron. When it becomes ionic, it will have a +1 charge, okay? Phosphate, not to be confused with phosphide, IDE, okay? Or phosphite, ITE, but this is phosphate. Now, that should direct you to the polyatomic ion table on the periodic table, and you will find that polyatomic ion to have the formula of PO4 -3 charge, okay? Now, that tells you that you're going to need 3 sodiums for every 1 phosphate unit. So the formula for sodium phosphate would be Na3PO4. Now that you got the right formula, you got 3 sodiums, 1 phosphorus, 4 oxygens, okay? With that information, now you can calculate the molar mass. And once you have the molar mass, you have the moles of sodium phosphate. So 5.0 grams of sodium phosphate, it equates to 0.03049 and more digits moles. We're not going to do any rounding up until we're done with the calculation. We have 255 milliliters. Remember that molarity is moles per liter. So we need to convert the milliliters to liters. So we know that in 1 liter, it is equal to 1,000 milliliters, okay? Note here, keeping track of your units. This is no different from what we've been doing. Keeping track of your units helps you set that problem up, because we're looking for moles, and when we have grams of a material, and if we divide by the molar mass, we end up with moles. the next step is to convert the volume to liters. And so given that conversion factor, we know that we want liters in the numerator, milliliters in the denominator. They cancel out, we end up with units of liters. Now, do the math, okay? And you should end up with 0.12 moles per liter. And so the molarity of 5 grams of sodium phosphate when dissolved in 255 milliliters of solution is 0.12 moles per liter. Okay, that is the molarity. All right, so don't forget the assignments as we talked about earlier. Okay, there is a practice final exam on the website. I also put it in, I believe, in the last module, module 15, so you don't have to go to our websites. They're in the modules. So yeah, use that as resources. And a reminder that since we're done with 15, we don't need to go into 15 again on Thursday, because this is the end of chapter 15. Congratulations, you have completed 15 chapters of chemistry. Okay, and it has been a pleasure. I will be here on Thursday, and if the 4:15 doesn't work out for you, feel free to come to the 1 o'clock. They're also doing a study day. And don't forget about the exam on Tuesday. And then don't forget that everything needs to be turned in by the 14th. And if you need to do the final exam at an earlier date, let me know as soon as possible so I can make that happen. Okay? All right. I don't have anything else